All right. Okay. I hope you guys are all doing well, healthy and well. And today, I thought we will take a look at optim, the function optim in R, and Nelder-Mead optimization. So we took a slight. We were talking about optimization back in like week 8 and whatnot. And then we took a slight detour to cover randomization tests and bootstrap because those are important topics. They're part of the course description. So I really wanted to make absolutely sure that we covered those topics. I didn't want to save them till week 10. All right? But there's still more on optimization that I want to cover. But this is, I would consider, like second priority in terms of topics in optimization. So we're going to cover them here, and we'll take a look. Okay, so the first thing is R has a built-in function called optim. Okay, it's a general purpose optimization function, and it's used to find the minimum of a function. So just like all of these other optimization stuff that we've been doing, we're looking for like a local min or local max, and optim will help us find a local min. If you want to find a local max, you just take the function, multiply it by -1, and then finding the local min will give you the location of the local max. Okay. This is how a call to optim will look like. So this is straight from the help file. It takes in the arguments par, fn, function, gradient, method, lower, upper, control, Hessian. Pretty much everything else has a default value, but par and fn do not. Okay, so par and fn, or par and function, are the two things that you must specify in the call for optim. Okay, and these are your two most important things, and then I'll talk about some of the other arguments. Okay, so par is going to be a vector of initial parameter values to be optimized over. Okay, fn, function, is going to be the function to be minimized, and we're going to spend a little bit of time talking about that. The function's first argument needs to be a vector of parameters over which minimization takes place. So you've got to figure out the vector of parameters, and you've got to write your function to be a function of that vector. Okay, and then the function has to return a single scalar value. That's going to be the value that you are trying to minimize, and so that is what the function will do. Okay, there's a couple other things: gradient, gr, and then method and control. Now, the default method is Nelder-Mead, which doesn't need a gradient, but some of the other methods, such as BFGS, CG, and LBFGSB, okay, these are, I think BFGS is it's like 4 people's names. BFGS is Broyden, Fletcher, Goldfarb, Shano. Okay, that's the algorithm, and it uses the gradient. All right, so basically, when we did unidimensional optimizations, one of the methods that we learned, or root finding, was Newton-Raphson, and we said, you know, you can apply this to optimization if you apply it to the derivative and stuff. But anyway, Newton-Raphson method uses the derivative. Right? You need the tangent line to find the root. You take the point, you find the tangent line, and you follow that down to the x-axis. And so you need the derivative to find the slope of the tangent line. And the gradient is kind of a multi-dimensional analog of the derivative. So, you know, the derivative gives you the slope. The gradient tells you the direction of steepest descent. So it's kind of like a derivative, but multidimensional. And these methods are basically gradient-based optimization methods. Okay. If the gradient is not provided, you can estimate it kind of numerically using finite differences. Much like in our class, I think I at least presented some notes talking about getting a derivative approximation, right? So if you can't figure out the derivative yourself, you can add like a small, like 0.0001 and see how much it changes to estimate the slope or the derivative. You can do something similar with the gradient. Okay, so that's what this is. So you can either provide a function that will calculate the gradient. If you don't provide a function for the gradient, then Optim will use finite difference approximation. Okay. You can specify the method. The default is Nelder-Mead, which we'll cover, but you can also use any of these others, BFGS, CG, LBFGSB, okay, and Brent. And then lastly, there is control, which allows you to provide even more parameters that will control the algorithm's behavior. So you can change like the epsilon or the tolerance for when it's going to stop optimizing and things like that. So you can specify all of that. Okay. And then the two arguments that you do have to provide are parameters and functions. Okay. So let me just show you an example. So let's say you have this function g of xy, where g is x squared minus 2x minus 0.5xy plus 2.5y squared. Okay. Now if you write a function, if you write this function in R, it might look something like this. X squared minus 2 times x minus 0.5 times x times y plus 2.5 times y squared. Okay, so that's what it might look like. Now this function will not work with Optim. Okay, if you try to plug this into Optim, Optim's going to error out and say it's not going to work. Okay, and the reason for that is because Optim needs all the parameters, all the variables to show up in one argument. And here, this function has two arguments. It has an x argument and a y argument, and it doesn't like that. So what Optim wants is it wants you to basically gather all the variables into one argument. Okay, and so it's very easy to do. It's very easy to do. But the first time you use Optim, and if you have no idea how to use this part's a confusing part, and it throws a lot of users off. Okay, so because it gives you a thing, and you're not quite sure what to do with the error message. So anyway, all you have to do is you just change the argument that goes into the function to just a single thing like par, okay? And par is going to be a vector of two values, all right? And then you just unpack par. You say the first value of par is x, and the second value of par is y, and then I just copied and pasted the exact same line down here, okay? So there's not a ton of difference between this and this, but this function will work with Optim, whereas this one will not, okay? So that's the key difference. And you can have a function of like 20 variables, okay? And you just have to put all 20 variables into that single vector par, okay? You put everything into that single vector par, and then you unpack it into all of these different things, okay? And then if you do that, then this function will work with Optim, all right? Okay, and then, and again, the value that the function returns has to be a single scalar value, which is what works here, okay? So once you specify it like this, then you can use Optim, all right? And so to use Optim, you call Optim, and then you provide parameters, par, and this is going to be, so remember, we have our vector par is a vector of length 2. The first is x and the second is y. And so here I'm providing just some initial starting values. These are completely arbitrary, it doesn't matter. But I'm going to set the initial values to be -1, 1.5, okay? But it could be something else, right? And we tell it the function is g, all right? So we've specified g right here, and so this will run, and then Optim runs and it returns this list, okay? The parameter values that will minimize the function is 1.025565 and 0.1024714. And then the value at the minimum is -1.025641, okay? It also gives us back the counts, how many iterations it took. It took us 85 iterations. And then convergent 0, that's what you want to see. Convergent 0 means it converged, no problem, okay? Sometimes you'll get other values like convergence 1 means it didn't converge, it hit the maximum number of iterations. And there's a few other things. The true values for the optimum values are 1.025641. This is found analytically, 1.025641, and 0.1025641, okay? And so we're getting close, but not exactly that, okay? And that's one of the things about the Nelder-Mead. Nelder-Mead will get you close, but it's not going to be like super precise. If you need something like accurate up to like a bunch of digits, Nelder-Mead may not be the best, okay? But it'll work. It doesn't require any derivatives or gradients to be found. It's a pretty clever algorithm, and we're going to talk about it. But it might not get you to the best values always, okay? Here is BFGS, so I'm basically the same exact call, I just changed method equal to BFGS, and when you do this, you can see the parameter values 1.02564110 and 0.1025641. So we get like pretty much almost exactly the values, okay? But BFGS requires calculating the gradient for us. We didn't specify a gradient function, so it's doing approximation. And just like Newton-Raphson, sometimes Newton-Raphson doesn't converge to a root, right? Like in your homework, you saw it like bounce around, especially if your slope was like pretty flat and stuff. Similar issues do exist with BFGS, okay? The 4 people who worked on it came up with a pretty good algorithm, but it's not 100% guaranteed, okay? It also converges faster, only requires 17 iterations, and it also achieved convergence 0, which is a good thing. All right, okay, with that, I do want to talk about the Nelder-Mead algorithm. The Nelder-Mead algorithm is a pretty clever algorithm. It's strictly computational, no gradients or anything like that required, okay? I am using the notes from Professor Henry Gavin. He wrote some really good stuff from Duke University, so I'm going to link to his notes. And what it does, what the Nelder-Mead algorithm does, is it iterates on a simplex, okay? And so a simplex is, I don't know, for lack of a better word, a shape, okay? And depending on how many dimensions you have, it's going to have n plus 1 of those. So if you have a function of 2 dimensions, it's going to have what we call 3 designs. If you're in 3 dimensions, it's going to have 4 designs. Okay? A design is basically a set of parameter values, and so for 2 dimensions, you'll have a triangle, 3 designs, okay? And each vertex of the triangle is going to have basically 2 parameter values, right? Coordinate and 2 space, right? If you've got a 3-dimensional problem, then your simplex is a tetrahedron. So it's a shape with 4 vertices in 3 dimensions. Okay, so that's like this pyramid-looking thing. And you know, each of those corners has 3 dimensions. And if you're in higher dimensional space, like 4-dimensional, we call that hyperspace, then you would have a 5-dimensional, I don't know what the tetrahedron equivalent is called in 5-dimensional space, right? You've got a hypercube and so I don't know, a hyper triangle looking thing, okay? All right, and what we're gonna do is we're gonna take our 3 points and we're gonna evaluate the function at the 3 points, okay? And then we sort the values, those 3 points, into from best to worst, okay? U is the best, we go U, V, W. U is the best, W is the worst. So W for worst, that's easy to remember, okay? And then as far as U being the best, just think of having a lot of confidence in saying U is the best. All right, okay. So, so that's where, just keep that in mind, all right? And we're gonna try basically these things, okay? We're gonna try reflecting, and I'll explain what that is. And if reflecting works, maybe we'll try extending, okay? And if reflecting doesn't work, then we'll try contracting. And if contracting doesn't work, then we'll try shrinking, okay? And I'll explain all of these things. And after each iteration, we'll check convergence to see if we should stop or not, okay? So, so what we're gonna do is we're going to take the worst point, W, and we are going to reflect it through the centroid of the remaining point. Okay, so actually, before I do all of that, let me just show you kind of a picture of what the Nelder-Mead algorithm looks like in 2 dimensions. So this is a simple thing that animation someone else made. So basically, we're gonna have a triangle. This is our simplex. Our simplex is a triangle, okay? And we're gonna basically walk the triangle to kind of where the optim is, right? The optim value is somewhere around here. We're gonna try doing this, okay? So I do this, and it's kind of just walking the triangle about, and we get closer and closer to somewhere in the middle, okay? Somewhere where the optimization value is, okay? I made another thing where I'm kind of label each of the steps, and you're gonna see it kind of go. All right. Okay, so let me just show you what all of these things do. All right, so here, the first thing we do is we are going to reflect the worst performing point through the centroid of the remaining points. We're going to call this reflected point R, and then we check the value of the function at the reflected point R. Okay? If R has a performance that is better than V, but not the best performing point, then we'll replace the worst point with R. If R is now the best performing point, then we'll try extending the reflection. So let me just show you what this looks like, okay? So this is our starting triangle, or our starting simplex, okay? All right, and so the optim is somewhere in the center here, right? So you can, the lines, these are contour lines, and pretty much all the points that exist on a contour line have the same value, okay? And so right here, the best performing point, okay, the best performing point is going to be here, okay? This is the worst performing point. This is slightly better, and this is the worst performing point, okay? And what we're going to do is we're going to reflect the worst performing point through the midpoint of the other 2 points, okay? So the midpoint of U and V is going to be like, I don't know, somewhere around here. This is going to be my midpoint, and I'm going to try reflecting W through here. So using kind of like a mirror, here's like that, and then I would end up, I don't know, somewhere like here, okay? And when I do this, okay, so this is what we can see, right? And when I do that, oops, this point, this is my reflection, this is the reflected point. Okay, so this is my worst. So we're going to reflect the thing, and what we're going to see is that the reflected point is the best point. Okay, it's better than U and it's better than V, right? So if we look at U is over here, and it's on this side of the contour line. And if we look at the reflected point, it's on the other side of the contour line, okay? This is a little bit more precise. So if we look at this dot, it's on this side of the contour line, which means it's closer to the center than this dot, okay? So this is now the best point, okay? And so when that happens, we're like, well, maybe I can be a tiny bit greedy, okay? And so we're going to actually try extending. I don't know what's going on here. Something. What is happening? Stop. Okay. Okay, we're going to try extending. We're going to try extending it, okay? And so I'm going to try taking this and going even further. So maybe like right there, okay? So I try extending it to somewhere like right there, and then we evaluate how well it performs there. And we say, well, this one performs even better, okay? So I think I extended it too far, okay? So it's something like that. This is my extended point. Okay, it's even better because it's even closer to the centroid, right? So, so we're going to take this. Extended point is even better. So we replace W with the extended point. Okay, so the next simplex is going to look like this. It's going to be these 3 points, these 3 things, and we're going to label these U, V, and W, okay? And so for the next iteration, this is going to be the best point U. So for the next iteration, this is going to become U. And then this one's the worst performing point. This is going to become W. And then this will be the next best point. Okay, so we're going to get U, V, and W. So that's going to be the next iteration. All right, so we can see this. So when I do this, we're going to accept this point. All right, and this is what our triangle looks like. And then we're going to evaluate these 3 points. And we're going to say this is U, this is the next best V, and this is the worst, right? Okay, so this is the worst point. And then what I'm going to do is I'm going to reflect it, okay? Is that okay? What happened here? So we started off with these 3 things, and this was the worst. We tried reflecting it. The reflecting was even better than the other points, so we tried extending it, and extending it was even better, so we're going to take that. Okay, so here, this is the next iteration. This is my best. This is the worst, okay? And so where will I reflect? Okay, I'm going to reflect through this midpoint, the midpoint of U and V. We're going to reflect W through the midpoint. So where will this take me? Okay, so this takes me from here maybe to around here, okay? And so I end up over here. This is going to be my reflected point. And if we look at this reflected point, okay, we're going to say, is U or R better? Okay, so what happens is U is still the best point, okay? R is the second best point, and V is going to be the worst point, okay? And so if R is going to be if the reflected point is the second best point, we just take it, okay? So the reflected point is the second best point, okay? So we accept it, okay? So we replace W with R, okay? And so at the next iteration, our triangle is going to look like this, okay? We've got U, R, and W, and then we will recalculate all of these things, okay? We'll relabel these. And so U is going to still remain U at the next iteration, okay? But R is going to become the second best, and V is going to become the worst point. Okay? That's what's going to happen. So we reflect it, we accept that, and then now we evaluate. And so this is my next triangle here. Okay. All right. So let's just see what if you guys are getting it. So right now we're just basically looking at reflecting and extending. So here, if I reflect, I end up over here, and if I extend, I end up over there. Okay. So I don't know if you guys can see this dot. This is the reflected, and this is the extended. So will I accept the reflected, or will I accept the extended? Which one's better? Here's the reflected, and then this dot is the extended. We're going to take the reflected, right? The reflected is better than the extended, right? So when I reflected, the reflected was better than U and V. And we go, oh, okay, maybe I can be greedy. So I tried extending it, but this is worse off, okay? So we're not going to take the extended point. So when we reflect it, we're going to accept this, and we take it, okay? And that's going to be this, right? All right. So here you've got, I've got left, right, and bottom, okay? Which one is the worst performing point? Left, right, or bottom? So you have to kind of look at the contour lines. Okay, and so if we look at the contour lines, the bottom is in between these two, and then the left is beyond this contour line, right? So the bottom is better than this contour line right here, and so the left is the worst. Okay, so when we label these, this is going to be the worst. Okay, and then we're going to try reflecting it, right? And so reflecting it will take me to somewhere around here. Okay, or I guess right there. All right, and then will I extend this, or will I take it, or what, right? Okay, so the rules for extending or not extending is this the new best point? This is not the new best point, okay? The best point is still this one, okay? So if this point is now the second best point, it's better than the worst, it's the second best point, and so I'm going to take this, right? So I can kind of walk my triangle this way, and I'll get a better performing triangle. This is the best, this is the worst, this is my second best point, okay? This is no longer the worst. So we're going to take that, and we get this, okay? So this is my best, second best, this is the worst, okay? I'm going to reflect the worst through the midpoint. Okay, so here I reflect the worst through the midpoint, okay? And now it's a little bit tougher. It's a little bit tougher to tell if this, we can see that this is better than the worst, but it's a little bit tougher to tell if it's the new second best or not, okay? It looks like it is, so we're gonna take it. All right, so here's, when I evaluate these, okay, this is my worst. All right, and watch what happens. Okay, if I try reflecting the worst point through the line, it takes me out to here. Okay, this point, when I reflect it, is even worse than my worst point. Okay, so if I reflect my worst point across and I get an even worse point, I don't want to take that. Okay, so that takes me to the next part of the algorithm, right? Which is, we've seen reflecting, we've seen extending, but if the reflected point doesn't outperform, okay, we're going to try contracting, okay? And so what contracting does is we're going to say, let's try 2 points, okay? Here's my midpoint. I'm going to try a spot in between the midpoint here and here, and I'm also going to try a spot right here, and right here. Let me let me label this. Okay. So this is the worst point, and this is U and B. Okay. And this is the R. So the reflected point is even worse than the worst point. Okay, so what we do is we will try 2 contracted points. We're going to try a spot right here and then a spot right here. Okay, so basically halfway, if we call this like our midpoint right here, we're going to try halfway between there, and then halfway here. So this is what we call our outside contracted point. And this will be our inside contracted point, okay? And then we look at these and we say, well, are either of these, which one's better? Okay, we're going to say, okay, the inside contracted point is better than the outside one, okay, and that improves our performance. And so we're going to take that, and so the next triangle, the next simplex will be this triangle here, okay? So reflecting didn't work. So if the reflecting doesn't work, then then we're not going to take it. Okay, so that's what happens. Okay, so we say, okay, reflecting didn't work. We try the two contracted points, and then so this is our thing here. Okay, let's take a look at this. All right, so here's this. I try reflecting it. Okay, should I take the reflected point? Okay, so if we look at the reflected point, it's better than the worst point, right? So if we look at the worst point's over here, and the reflected point is over here. The reflected point is better than the worst point, okay? But the reflected point is this triangle. If I do this, this triangle is still going to be the worst point. Can we see that? So this is my worst point, okay? And this is a reflected point, okay? The reflected point is better than the worst point. Okay, but it is still going to be the worst of the 3 points. Okay, does that make sense? All right, we see that? So what's going to happen is that if I take this and my next simplex is this, what's the first step it's going to be? The first step will be reflecting it back, and we're going to get back our old worst point, okay? And then we're going to say, well, that's even worse than what I currently have. And then so what we'll do after that is we're going to try contracting it, okay? So it seems a little silly to reflect it, get a point that's a little bit better, but not better than the other two, so that the next step we're going to reflect it back, get our old worst point, and say, okay, the next thing is to contract, okay? So what we're going to do is if we reflect it, and even if it's better, but if it's still going to be the worst of the 3, we're going to just go straight to contracting, okay? So still going to be the worst of the 3 points, so we go straight to contracting. There's no point in accepting this, reflecting it back, and saying, oh, this was my old point, right? Because we reflect the worst point. So we're going to go straight to contracting, and then we would get our outside contracted and our inside contracted, and then we're going to take the outside contracted point. Does that make sense? So that's what we're going to see, okay? So we say this and we go, okay, let's just go straight to contracting, and it's going to take the outside contracted point, and it gets that. All right, and we can, and this is pretty much the algorithm. There's one more case which we don't encounter in this, and that's going to be shrinking. That's even after you try contracting, if all the contracted points are still going to be the worst point, then don't take it. Okay, so, oops. Okay, so this is the worst point. We try reflecting. That's not going to give us anything better, so we try contracting, okay? And then we say, okay, if I contract, this one's even better. So we shrink there, okay? Now we can see this one's the worst. We'll try reflecting it. Okay, that's not going to be better. So then we'll try our 2 contracting, okay? We have an outside contracting and an inside contracting, and we can see the inside contracting point is better. So we take the inside contracting, okay? And here it's hard to tell which one's the worst, but I think this one's the worst out of the 3. Okay, and we'll try reflecting. Reflecting gives us even worse performance, so we'll try contracting. And I think it's going to be clear that the inside contracting point is going to be the better one. So we have 2 inside contracting, and then we take the inside one. Okay, and then we just can let it continue, and the simplex just gets smaller and smaller, and I think I have it arbitrarily stop here, okay? Just for the sake of this thing, okay? So again, starting there, we try reflecting and extending. here we reflect and accept, we reflect, extend, we take the reflected point, we reflect, and we take the reflected point, we reflect, we take that, we reflect, we don't like it, so we contract, we reflect, we don't like it, so we contract, we reflect, we don't like it, we say contract, and so on and so forth, okay? So in some cases, so here we reflect and we contract again, and in this case, we tried reflecting it, reflecting was even better, so we tried extending it, extending was no good, so we're going to just take the reflected point, okay? And then we just let it run. And we can see that it gets closer and closer to what appears to be kind of the middle of this contour plot, okay? All right, and so the neat thing about the Nelder-Mead algorithm is that even though we saw it work in 2 dimensions, it can work in higher dimensions, okay? And you know, my picture drawing skills aren't super great, okay? But you can imagine kind of having 3, you know, a simplex of 4 values here, okay? All right, so this is supposed to be like a pyramid, okay? We've got something like this, right? Okay, and you know, let's say this is our worst, let's say this one's our worst performing point. Okay, and so we're going to take a look at this, we're going to reflect it through this pane, okay? So this plane, which is kind of this surface here, okay? We're going to take the centroid of this surface, which I'm not quite sure. Is this the centroid? I guess I can kind of try to figure this out. So you take it to the midpoint of this line and the midpoint of this line and the midpoint of this. Should be something here. So this is going to be the centroid right there. So this is the centroid of the plane. And then we would reflect the worst point through the centroid, okay? So we're going to kind of just reflect it through here. And so our new centroid, or our new simplex, like assuming this is, if we take the reflected point, okay? So this is our reflected point. And then you can try all of them, right? You can try extending it or contracting it. And then your next simplex will be the tetrahedron with this, okay? Something that looks like that, okay? And you would keep going, and hopefully, you know, one of the other points, maybe this is going to be like the new worst point, and then you'll reflect it through this pane and things like that. And so this Nelder-Mead algorithm, as kind of as simple as it is, can generalize to higher dimensions, okay? And so here is, again, these are the kind of the 4 things that we might consider. First, we sort them and we find the worst point. We reflect the worst point through the midpoint. If that works, then we'll try extending it. And if that doesn't work, we'll just take the reflected one. And if reflecting doesn't get us anything better, we try contracting it, okay? And this is what we saw in our video. If the contracted points are still going to be the worst, then we can just try shrinking the simplex, okay? And we didn't see this, but shrinking the simplex means basically moving V from here to the midpoint of UV, and then moving W to the midpoint of this edge, UW, okay? And you'll get a smaller triangle. And this usually happens only when you get close to the very end, shrinking, okay? And then here's kind of just what the picture looks like. So here we tried reflecting it, and then we ended up extending, and then from there we tried reflecting, but we didn't like that, so we contracted, and then we reflected, and then extended, and then we reflected, and then it looks like here they did reflecting, and that didn't work, and so I think they shrunk, and then from shrinking and so on and so forth, right? So anyway, I'll link to this. This is a very good paper that covers the kind of the tutorial on it, and I hope this little animation is helpful as far as how the values that it's evaluating to move from some arbitrary starting location towards something close to the center. Okay, and all you're doing is you're just figuring out which one's the worst, and then you're just kind of trying to leapfrog walk your triangle around to get something better. Yeah.
How can you tell from that graph how the 3D contour is?
So the contour lines represent values that are that have the same, or are locations that have the same value, right? So it's kind of like, imagine having this shape, and you're gonna put it in a tub of water, and you pour some water, and then you draw the water level, if that makes sense. Okay, where I don't know, let me see. Contour lines visualized. Okay, so here you've got some shape, and then in 3 dimensions you draw this, and when it gets flattened down, this is where this is what the contour map looks like. Okay, and so where you see these flat lines, or not the flat lines, where you see these lines represents locations that have the exact same height or altitude or value of the function. Okay, so I guess here's like another, they're all kind of similar pictures, because this is commonly used in topographical maps to show geography, to kind of show. So if you so one thing to note is that if contour lines are bunched very close together, okay, so let me see. Okay, so something like this, where you have a bunch of contour lines really close together, this indicates a very steep area, okay? Because each contour line basically means you are changing values, like in this case altitude. Maybe each contour line represents 100 feet, okay? And so when you're just going from here to here, you have gained maybe like 500 feet in elevation or something, okay? And then whereas over here the slope is a lot less, because you travel a much greater distance to kind of gain 500 feet in the elevation as well, okay? So for your elevation to change, you have to kind of cover a larger distance, whereas if the contour lines are really close together, that indicates an area where it's really steep, okay? So anyway, on this animation, it just shows, so this area is fairly steep, okay? And then this area is fairly, is a little bit flatter, okay, as far as the bowl goes, yeah. Okay. All right, that's all I had for you guys today. So stay safe and healthy out there. Please vote in the poll if you haven't done so already. And we'll see you guys on, well, maybe. We'll see you guys on Wednesday, maybe. So, all right.